Assalamu alaikum. Welcome to lecture number 30 of Software Requirements Engineering CSE305 and in today's lecture we are going to talk about methods for requirement engineering. This topic we started discussing in our previous lecture, and we said that first of all we tried to define what is the role of method, and then we said that by using a different method we are going to generate different system representation, and that is how we need to look at these methods, that each method follows the same requirement engineering processes, but the emphasis on different processes would be different and the output would differ. So that is what is meant by when we talk about these methods for requirement engineering. So let's quickly recap what we did in our previous lecture, and then we'll continue with our discussion on these methods for requirement engineering. So in our previous lecture we concluded or finished our discussion on requirement engineering for agile methods. We were talking about, we spent almost 2 lectures on this particular topic. So why it is important to look at these agile methods separately? The reason is that huge amount of a large number of companies, specifically in terms of Pakistan or our local software industry, they are following these agile methodologies, and although they are not following it in their true essence. As I said, that people generally have wrong perception about agile methods, and they actually think that they know agile methods and they are very informal, whereas people who thoroughly understand an agile method, they would know that agile methods, they are more formal than other models, and we need to stick to different disciplines of a certain agile method. And we said, we looked at the different examples of agile methods. There is extreme programming, there is feature-driven development, there is Scrum, and there are lots of other models. And whichever model you pick, whichever model suits your context. Remember, we talked about that you pick a model checking its suitability from your context, and then you adapt it, and then you change it depending on your needs. So whichever model you pick, you need to follow all the practices of it, because in general, all the agile methods, they are based on this principle of lean production. So we know that the idea is to remove the waste, identify the waste and remove the waste. And by waste we mean that anything that the client does not want, we do not want to do. So we only want to do something which people actually want from us. So, but having said that, you cannot be ad hoc about things. So for example, that is why we looked at a particular agile method in a previous lecture. We talked about extreme programming. And we said that extreme programming has certain principles which it follows. So number one, first of all, we tried to establish that how it is an agile method. Why it was an agile method? Because it follows certain agile principles, because it has frequent or small increments, it involves customer, and it incorporates changes. So we said that, and it believes more in people than processes or tools. So we said extreme programming is an agile method because it follows all those agile principles. But here we are trying to discuss that how extreme programming, or how when a company or a software house or certain people, they are following extreme programming, how do they engineer requirements? So we said that, and we discussed different things that are done in agile. So firstly, we remember we discussed that in one of our lectures, that requirement engineering in agile methods is based on 2 main concepts or principles. So the first concept was waste reduction, and the second one was evolution of requirements. And then we started looking closely at these different principles or these different concepts which are there in extreme programming. So we looked at customer involvement, and we said that customers are involved in extreme programming in 3 ways. They help you in identifying the user stories or develop the user stories. They are part of the negotiation and prioritization process. When you have those different user stories, customer would help you prioritize, okay, this is what I want you to do in this particular increment. And then customer are also part of the process when you are developing those acceptance test cases. So this huge customer involvement actually ensures that you are reducing waste, and we talked about it. Similarly, then we talked about requirement scenarios, that how user stories are generated and what is the purpose of generating those stories or writing those stories in small cards. And we looked at a particular example We said that a card can be of this shape, where this is the title of the card. And remember, we talked about that waste reduction is achieved by frequent increments and splitting the requirements. So in a user story or one story, it belongs to one process, or it should talk about one set of features. Remember, the example that we discussed was downloading and printing an article. So it had all the different tasks which your system needs to do in order to actually complete that particular functionality. So there were different tasks in it. The first one was displaying an article, then selecting an article, displaying the payment options, and then the payment process as well. So there were different tasks. And we said that those different tasks are then taken by developers, and they do their time estimates. And those estimate, those schedule and cost estimate, they are used in the process of when you're prioritizing those different user stories. And then we discussed changes and refactoring, because we know that there are two agile principles on which requirement engineering is based in agile methods. One is evolution of requirement. So requirements are going to change. So, and that is very true with agile, with extreme programming as well. So in extreme programming, maximum size of an increment is 2 weeks, and customer requirements can change very frequently. So it means that the code would become very messy. So because we are not spending too much time on planning, because we are just very responsive to those change requests. So whenever a change comes in, we implement the change. So it would mean that our code would become very untidy. So we need something to make our code more readable, make it more efficient, and there's a process called refactoring. And then we discussed that how refactoring actually works. That when we refactor our code, the basic concept is that you do not change the functionality. So the assumption is that you're refactoring your code, but you're not changing functionality of the product. So that is, and then we talked about testing and how testing in extreme programming helps us in requirement engineering. So we said that extreme programming testing is based on that principle of test first development, that you develop the test cases first. So developers are responsible for testing their code. So before each developer start working on his task, he or she would have to define the test cases for it first. So by doing so, you are validating requirements. So you're removing all the problems with the requirements before you are developing. So you're removing waste. And so testing, so we looked at all these things that are there in one particular agile method, and how requirements can be engineered by sitting in a particular agile method. We looked at that. So that was our discussion on requirement engineering in agile methods. And just to conclude, we talked about different sub-processes of agile of requirement engineering in detail. We talked about inception, elicitation, elaboration, negotiation, specification, validation, and requirements management. So if you look at these agile methods and that particular example of extreme programming, we can actually see that all those processes, they do exist in these agile methods as well. It's just that they have different names, they have different definitions, and the amount of detail is different, but they are all there. So there is elicitation, there is elaboration, there is specification, there is negotiation, there is validation, and there is changes as well. So they have all these processes. So all that information is useful, even if you are using these agile methodologies. They are just different names for it. But remember, whenever you are following agile methodologies, you need to be very formal, and whatever model you pick, you need to stick to it. You need to follow all the practices of it. And then we started off with our next topic, which was methods for requirement engineering. And we said that first thing we tried to establish is that why we want to worry about these methods, or what is the role of these methods. And we said that depending on different method you pick, you will follow a different process for requirement specification, or for requirement engineering. And the system representation in form of system models, it would vary as well depending on your choice of method. So a different method would produce different kind of system models. For example, data flow modeling would result in data flow models or data flow diagrams, DFDs. Similarly, if you have semantic modeling, it would result in maybe entity relationship diagrams. If you have object-oriented method, then the system models would be object diagrams, class diagrams, and these kind of things. So your choice of method for requirement engineering would mean that your system representation is different. And we looked at different models. We looked at data models, we looked at semantic models, and we started our discussion on object-oriented methods. And we were discussing, so this is what we are going to do today as well. We are going to discuss, continue our discussion on methods for requirement engineering. And this is where we left off. We looked at what is an object, or we looked at an object definition. And now look at this class definition. So an implementation of an object type, the object type, for example, bank customer, refers to a class of bank customers. So a particular, so and what is an object? An object is an instance of a class. Okay. So for example, we have this whole class customer, and from this whole customer class, one instance can be any one particular customer. So each customer might have an ID, he might have a name, and he might have a different, they do have different NIC numbers, they have a different address, you know, all these information is different. But they are instance of a particular class, which tells us that how this object would be enacted in real life. Okay, so that is the relationship between object and a class. So objects that share common attributes and operations. An object is an instance of a class. For example, as I gave the example, you know, John Smith, or you know, you can make any other name, or Naveed Ahmed is a bank customer. Then bank customer is the class, and John Smith is an instance of that bank. So for example, we have this customer class, and one instance of that class is, for example, Naveed Ahmed. So that is one instance of that customer class, or any other name. So there can be multiple instances. They can, all the customers, they are all the instances of this particular customer class. Then we know that each class has different operations and methods. And what are these? They are used to read and manipulate the data of an object. Reference only the data structure of that object. To access the data structure of another object, objects must send messages to that object. So normally what happens is that these objects or these classes, they do interact with each other. So operations are used to manipulate the data that is stored within a particular class, but you also need to send messages to other classes, because there are certain functionalities which you cannot do on your own, and that is also done. So methods specify the way in which operations are encoded in the software. So what is this? We said that there are different concepts. So what is this concept of encapsulation? So encapsulation means packaging together of data and operations that manipulate the data. So when we have this class, then we encapsulate the data, and we also put operations in it. So these operations work on in this data. So details of how operation is performed is hidden from the user. Prevents the unauthorized access of an object's data, and this you guys should have covered by now in your courses on object-oriented programming in detail, I guess. And then there is this concept of inheritance as well. This you can also show in system models when you're generating system models for requirement engineering. So objects at a lower level in class hierarchy inherit the operations and attributes of their parent class. Objects are able to incorporate data or operations specific to themselves. Inherits data from more than one parent is called multiple inheritance. So that can also be done. So this is an illustration of a class and an object. So let's say this is the class, which is the library item. It has different attributes and it has different operations. And then this is the object. So normally, whenever you make an object of a particular class, then it inherits all the things of a class. Okay. So for example, you say that this particular object is a book, and the book has author, publisher, year, and it has these operations as well. So we have this concept of encapsulation as well here, which you can see. So messages, what are these messages? Objects communicate by sending messages. Message comprises of name of the receiver object, operation to be invoked, an optional set of parameters. So when an object receives a message, it causes an operation to be invoked. The operation performs the appropriate method and generates an output. So this is how this message passing in none. For example, we have these two objects, object X and object Y, and they can be of different classes. So what we are doing here, that message 1 to object Y and operation 12 and parameters are passed, which are parameters, for example, A and B. and on the basis of this message, this particular operation will be invoked. So look at that library example again. We saw that library example for data flow modeling and how a different system model is generated when we pick a different method for requirement engineering. We look at now object modeling. So our library system is intended to provide its user with the ability to automate the process of acquiring library items, cataloging library items, borrowing. So these are the functionalities that we want. So library items comprise published and recorded material. The system will be administered by a member of the library staff. Users must register with the system administrator before they can borrow library items. So these are the things that we normally, and there's some more detail about this library example. Library users are drawn from 3 primary groups: students, member of staff, and external users. So we'll see that there should be a bigger class which we will call a user, and different classes would inherit different properties of that class user. So student would be would have a superclass user, member of staff would have the same superclass user, and external user would have the same superclass user. All the library users have, as part of the registration, a name, library number, and address and account. In addition, the following information also required for registration. Students, for example, when it's a student, the degree in which the student is registered is also need to be known, and admission number. And for a staff number is unique, and for an external user, employer detail, they are unique. So what are the steps that you follow when you are using this object-oriented method for requirement engineering or for generating system models? So the first thing that we do is we identify core objects. So from this description of this example, of this library example, what we are going to do, we are going to identify the core objects. We construct the object structures, defining the associations between object classes. So this is somewhat similar to what we have already discussed during analysis. If you remember that we identify those potential classes, we try to, from those potential classes, we try to define that these classes would be part of our final solution. And then we try to also define that how we are going to communicate with each other. So that is what we are doing. So we say that we identify core objects, we construct the object structures, defining the associations between object classes. We define the attributes associated with each object. So we relate those attributes to different objects. We determine the relevant operations for each object. We define the messages that may be passed between different objects. So these are all the things that we do. So this is how a class is represented. We have class name, we have list of attributes, we have list of operations. Then this is how a generalization is shown, and this is how another type of association, which is called aggregation, is shown. So this is the step 1, which identifies, remember there were 5 main steps, that we identify the classes or objects. So we have identified that library user, library item, library staff, and account, these are the objects or classes in my system. So we can identify the following relationships from the partial requirements. Our library users borrow a library item. So if we go back, our library user, he borrow a library. So we know that there is an association. So by identifying these relationships, we know how these objects or how these classes are going to talk to each other. Our library item is recorded or published. The system administrator registers the library user. So we know again that library user is going to get registered by a certain library staff, which is an administrator. Library users and students, staff, and external are, so who are the library users? We are defining that student, staff, and external users, they are all the library users. So there may be subclasses of this particular class, which is library users, and they can be students, staff, and external users. And then we say the system administrators catalogs the library items, the library assistant issues the library items. So this is the basic object model showing attributes and the relationships. So we say that we have this library user, we have library item, we have account, and we have library staff. And here we have not put more detail here. We put all the library staff in this one class. We say that administrator is also there, and any other library assistant is also there. And for each library user, we identified that for each library user there will be name, there would be library ID, and there will be address. So, and we identified the relationships between them. We said a library user can borrow a library item, library user browses library item, library user registers with this library staff, and with each library user an account is associated as well. And then we have this library staff, it catalogs the library items, he receives, and they also issues. So by identifying those different relationships, we know that how these classes are going to talk to each other. So all these links between them, these are called associations. So we know that these are all associations between different classes. And as I said, that depending on the problem description, we knew that some classes might be inherited from our superclass, which is this library user. So this is our superclass, and this will act as a parent to all these classes. So library user, staff, and external, they are specialized form of this parent class, library user. All these three classes, they inherit all the properties and operations of this class. So a student, so it is incorrectly written library user, so it will be student. So each student would have a name, address, and a library card. Similarly, each staff member would have a name, address, and a library ID. And external users would also have these three things. But they also have additional information which differentiates these different classes. Because for a student, we need to know what is the degree program in which he is registered and what is his admission number. For a staff, we want to know what is his staff number. And for an external user, we want to know employer name or employer address as well. And because this library user meant that for each of these users, we are going to maintain this account. So these classes, they also inherit those associations as well. So this actually is the same as if we say that a student has this aggregation with this account. So this is the same. And so either we do that, or so this is a more efficient system model where we have defined a superclass, and our inherited classes, they are inheriting all the things that superclass had. So all the attributes, operations, and all the associations, they are inheriting. So similarly, inheritance for library item. So library items can be of two categories. We have these published items and we have recorded items. Again, remember that we are generating all this information from the description that we had, or the different types of relationships that we identified. And then within published items, we have multiple categories. We have a book and a journal. So each published item has a title and a class mark. Okay. And each library item has these things, and library items has two categories. So there are two kinds of categories, that two types of library items. There can be published items and there can be some recorded material. So both of these would have these two common things, but they have some additional thing. Published items have a publisher and a year of publication. Similarly, recorded items have a certain format, length of the video or an audio, whatever the recorded item is, and detail of its contents. Similarly, there can be multiple types of published items, and each published item has these two things, but depending on the type, they might have different things. For example, a book would have an author or list of authors or an ISBN number, but a journal would have a volume and issue as well. So this is how we put more detail into the system models that we make. Then step 3 was identifying the attributes. Attributes can be revealed by analysis of the system requirements. For example, it is a requirement that all the library users must be registered before they can use the library. So this means that we need to keep registration data about library users. So library users may also be provided with an account to keep track of items loaned to them. So again, from the requirements, we put more detail in the model. So we get the information from there. So library items has the attributes title, description, and class mark. Again, this is written in the description of the system. The library user class has the attributes name, address, and library ID. Again, this was mentioned when we started looking at this particular library example. And then step 4 was object operations. This step is intended to describe the operations to be performed on the objects. Certain operations are implicit from the object structure. These include operations for accessing and modifying the attribute values. For example, if you look at the student degree program and admission, we would need some operations to actually manipulate that. So these are implicit. When we look at that class, we know that we need these operations. One way of identifying operations is by modeling the messages that may be passed between the objects. As we have just said, that if we model those messages that will be passed between those different objects, then we would know that what operations are needed. For example, if we issue a certain book, then our account needs to reflect that we have a new book. So by identifying those relationships, we know that we need an operation which automatically updates my account as well. So there would be message passing between your class and your account class as well. So for example, here is this library user. Whenever he issues a library item, he can issue a library item, he can return this library item, and he can browse. So we know that these are the three operations that this or instance of this class or an object of this class library user will perform. And whenever this particular operation is performed, there will be a message passed to this particular class library item that update your record. Okay. Similarly, library staff is also going to talk to this class library item, because whenever a new book comes in, he is going to catalog it. If they are going to dispose any book, then there is an operation dispose, which would actually mean that a certain item is removed from this library, and library staff, so an object of this particular class is going to perform these operations, and whenever these operations are performed, certain messages will be passed to this particular class. The same is the case with this relationship, where we are saying that an instance of this library staff class is going to register users and is also going to query on their accounts as well. So that is how we now we know that how or what are the operations which are performed by different objects. We can update our model. So now the updated model would look something like that we have this library user class. Now these are the two things or the operations of this library user: register and query. And then we have this class again, and then we an account class would have another operation, which is compute file. So operations for library items mean that we are acquiring, issue, return, dispose, and catalog. And similarly, we can identify the operations for rest of the classes as well. Then use cases and event scenarios. Object operations may also be identified by modeling event scenarios for the different functions provided by the systems. Events are then traced to objects that react to them. Typically scenarios model the interactions between the users and the system. So use cases are also a very useful way of actually doing that we model different events and scenarios, and we trace those events and scenarios to generate those object models. And this we have covered when we talked about object-oriented approach, and scenario modeling was one of the modeling that we do in it. So our library user, they access services, and when they are accessing services, they use this authentication procedure as well. And library user, another use case with a library user, another interaction of a library user with the system is that they can browse items. Similarly, when we talk about library staff, they can register users, and it also means that they can change the permissions as well of different users. So event scenarios. So what are the event scenarios for browsing items? So for example, we have this library user. So the first event that he would generate to the system is that he would request for a certain library item, and then the library staff, what he would do then is, first of all, he would try to validate that particular user, that whether he is a valid user or not. If he is not registered, then he is going to request for registration, and then if the registration is accepted, then the library user is actually going to verify that whether this particular item can be loaned to this user or not. So we can also model those events, that how different objects are going to interact with each other. So the first thing, so whenever you go into a library, you present your library card and you say, this is the book that I want to issue. And first of all, the library staff would check whether you are a valid user or not, and whether your account permits that a certain book can be issued to you or not, and on the basis of that, the book is issued to you. So by modeling these certain events, or these event scenarios, you can identify different operations that an object would perform. And then this is a very interesting topic, and this is the final method for requirement engineering that we are going to talk about, and this is the formal methods for requirement engineering. And I know that in you guys have in your curriculum another course on formal methods specifically for software engineering, but we are going to talk about formal methods for requirements engineering. And why, first of all, why do we need these formal methods? Again, the different types of methods that we have discussed so far, they generate system models, but the informality in those models stays the same. Whereas these formal methods, they are a completely different class of methods. So normally what happens that all the semi-formals and informal methods that we have discussed, they use natural language, diagrams, tables, and simple notation. So we have seen that, data flow diagrams or entity relationship models, or those data models, semantic models that we discussed object-oriented models. So all these methods, they have these representations. Either you write requirements in terms of natural language, or you make these diagrams. Whereas these formal methods, they are based on mathematically formal syntax and semantics. So there is no ambiguity. So either something is true, or something should exist, or it should not. So there is no ambiguity. So whenever you write something formally, it has no ambiguity in it. So that is the biggest advantage of using these formal methods. But the problem with using these formal methods is that they are very expensive. And expensive, why I say they are expensive? Expensive in a way that normally there are very few experts, first of all, and at times it is not possible to use formal methods to specify all the requirements of a system. The reason is, number one is that you do not have the resources to do that. Secondly, it would take you a lot of time to actually specify requirements formally. Although it will ensure that you have no ambiguities, but it will take you a lot of time. So normally formal methods are not frequently used for day-to-day systems. But for critical systems or for critical functionalities of a system, remember we discussed critical systems. So again, all the requirements of the critical systems would not be formally specified. But formal methods would be used for some of those critical functionalities, on which the system actually relies upon. So there would be some things which you would want to specify formally because you do not want any ambiguity in them. So as I said, that all the semi-formal and informal methods that we have discussed, they use natural language or tables or different kind of diagrams, whereas these formal methods, they are based on mathematical notation. And then there are different languages which people have proposed to write requirements formally in them. We are going to look at one particular language, which is Z language. There are also there are other available as well, as it is said here. VDM and Lotus and B are other examples of formal methods. So these formal methods, they provide a means for achieving a high degree of confidence that a system will conform to its specification. Okay. So this is the only method that ensures that whatever you have written is right, or whatever you have written, there is no ambiguity on it. So, but again, do not absolute guarantee of correctness. Still, I mean, we obviously say that there is no guarantee of correctness. Have little or directly to offer to the problems of managing software projects. However, benefits can be gained from gaining a clear understanding of the task at an early stage. As I said, that in general, they do not actually provide you lots of benefits, in terms of, managing projects, but the main benefit is in the form that because you are defining and specifying things formally, so you are removing ambiguities. So when there are no ambiguities, then remember, that with software requirement engineering, lots of things or lots of processes were there because we said that there are ambiguities in the requirements. For example, we had negotiation there, we had analysis there because we knew that there are problems in the requirements. And similarly, we did validation because we said that there can be ambiguous requirements. So if we are specifying these requirements formally, then we will save a lot of time in those things. So it's kind of a trade-off. And as I said, you do not write all the requirements of every software formally. Normally for day-to-day software or for smaller projects, formal methods are not used. Their use lies with those critical systems, and you cannot model all the requirements formally of all the requirements of the system formally. So you would choose that, okay, this is the critical feature, I need to write this formally. So this is how they are used. So what are the components of a formal specification language? So as I said, that there are different languages which people have proposed to write requirements family, and they vary on notation. So their notation would vary from one language to another language, but they serve the same purpose, that you are trying to specify requirements in a mathematical format. So what are the components of formal specification language? The syntax that defines a specific notation with which the specification is represented. Semantics that help to define a universe of objects that will be used to describe the system. And the relations which define the rules that indicate which object properly satisfy the specification. So these are the three main components of a formal specification language. You have the syntax, you have the semantics. So you have the syntax, that this is the syntax that you are going to, and which notation would be used when, and then you need to understand the semantics of that, of those statements, and then the relations. So these are the three main components of a formal specification language. And as I already discussed, that formal methods are not widespread. Factors contributing to slow acceptance of formal methods are difficulty in understanding the notations. As we will just see, it's not very easy to actually specify requirements in this fashion, and it takes a lot of time. So that is a bigger problem. And remember, we said that the requirements that we write, or the SRS or software requirement specification document that we produce, there are lots of users of it. And then when we are specifying requirements, at times the system models are generated, or these requirements are written so that all the other people understand it. So if my customer is not capable of understanding a formally written set of requirements, then why would I do it? Or so that is the main reason. And maybe the developers, designers, they are not familiar with it. So there is difficulty in understanding the notation. That is one of the biggest problems why the acceptance of these formal methods is so slow. And difficulty in formalizing certain aspects of requirements. Again, at times it is not possible to formally specify everything in the product, and payoff is not obvious. So you cannot actually tell that what is the payback that you're going to get if you specify requirements formally. You can say that you're going to save a lot of time because you are removing ambiguities, but you cannot actually put a dollar value to it. So it's not very easy to actually do that. So the number of formal languages in use today can be broadly divided into two categories. So there are different categories of these formal specification languages. We have model-based notations, and we have process algebra-based notations. And in our discussion in this particular course, and in today's lecture, and in our next lecture, we are going to look at this model-based notation, and specifically, as I said, we are going to look at Z language. So what are the advantages of formal methods? Although we have already discussed this, so let's formally write that these are the advantages. So number one, it removes ambiguity, as we have said, that when we are using this formal mathematical notation to write requirements in the form of maybe discrete maths constructs, we are using that, so we are removing ambiguities. It encourages greater rigor in the early stages of the software engineering. So remember, we said that early on in the product, customer is not clear about requirements. So let's say we stick to it. Now, no, we have to use formal methods. Then you are putting a lot of rigor in early stages. So you will spend a lot of time in understanding and removing the ambiguities, because you want to write it in a formal way. You want to write in a Boolean way, 0 or 1 way. So it cannot be done if you do not have clear understanding. So if you're using these formal methods, then it means that you will need a greater rigor in early stages. So possible to verify the correctness, incompleteness, and inconsistency checking of the specification. So whenever you write requirements formally, then you can check your formal method for these, formal model for these things. You can check it for correctness, you can check it for incompleteness, and you can also check it for inconsistent. So whenever you write, you are using a particular language. For example, we'll see the examples of Z language. if we are specifying requirements using the Z language, we can actually check it. There are different tools. There is a tool with the name Z-Avis. So there is a tool with the name Z-Avis. You can write requirements formally using Z language in this tool, and you can automatically check whether the requirements that you have written, whether they are consistent, correct, or incomplete. So that is so these are the advantages of formal methods. And if you look at these advantages, as I earlier mentioned, that if we are removing ambiguity, if we are removing all these things, then all the time that we spend in analysis, validation, and negotiation, all these things are done at different stages. So maybe we are doing all these things with elicitation early on. And remember when I said that, when you pick a different method for requirement engineering, your timing of different activities that you do in requirement engineering, it would vary, and your emphasis on different activities would be different, or the way you are going to do it, it is different. So when we are using formal method for requirement engineering, we are doing these things, but we are doing them at different times and in different fashion to generate different kind of output. So disadvantages of formal methods: difficult to represent behavioral aspect of the problem. Some requirements can only be determined through empirical evaluation and prototyping. So you cannot, even, it does not matter how much rigor you put into early stages, you cannot just specify those requirements formally. Do not address the problem of how the requirements are constructed, and lack of adequate support tool. So that is another problem. So now the Z language, which is a model-based formal language, as I said. So we are going to emphasize on this particular language. A Z specification is presented as a collection of schemas. So what are schemas? So it has multiple schemas. So a schema comprises three main parts. You have the name of that schema. So any schema that you would write in Z, it would have a name. So name is written. Then it has a declaration portion, and it has some predicates. So these are the three things. So each schema that you're going to write in Z, it has three things. It has name, declaration, and predicates. Schema declarations set out the names and types of the entities introduced in the schema. Schema predicates set out the relationships between the entities in the declarations. So name is simple, that for example you say library user, that is the name of your schema. Then in the declaration you will list all the things that you need to represent this user, and in the predicate you will identify different relationships between those entities that you have already declared. So using Z language, variable declarations are of the form identifier and the type. So you first write the identifier and then the type. Predicate give properties of and relationships between the variables. A schema may be used to describe either a state or an operation. So a schema can be a state and an operation as well. So schema is not just an operation. So for example, remember that library user that we were talking about. So adding a user, deleting a user, those would be two different schemas. Those are operations. But there would be a journal schema where you would describe just the state, where you will just define who is a library user. So that can also be a schema. So to describe a state, the declared variables from the components of the state and predicate give the invariant properties of the state. For an operation, the declaration consists of the initial state components, the final components, the input and the output of the operations. So when it's a state, we are going to define that how the state is defined and what can be the possible values, or what can be the possible values that what are the possible states that that these variables can have. But when we are defining operations, we will define the original state of the system, and we will define the output, and that on the basis of what input, what would be the final state of the system. So this is what these schemas would vary on, if it's a schema for a state or if it's a schema for an operation. So this is how a Z schema looks like normally. So you have this schema name, then you have these declarations, and then you have these predicates. So this is again that same library example. So we say the state space of lending library can be defined using the following schema. So we are saying that, so this is the state space. of the lending library. So remember that this is not an operation. So we are saying that we have a stock, and what is the stock? So remember we said that we have the identifier and then we have the type. So stock is of the type books. Okay. And then we are saying that on loan is something which tells us that whether the book is on loan or not. So this is actually telling us if we want to see that whether a certain library item is on loan or not, then we are specifying that if a book is on loan, then there would be a borrower associated with it. So it cannot happen that a book's status is on loan and you do not have a borrower against it. Okay. So when we write it in this fashion, so we are clearly stating that this state cannot happen, that you have a loan book and there is no borrower. Okay. And then loan, whatever books there can be loaned, they should be a subset of the stock. So you cannot loan a book if library doesn't have it. So it should be a subset of that. So this is how we define the space or the state space of this library example. So, and this is the borrow operation. So remember we said that we have this state and that we have this operation. So there are two types of operations. There are operations which intend to just read the state, but there are operations which modify the state. So for example, we have this borrow operation. So whenever there is this borrow operation happens, then this delta signs, it is actually telling us that the state space is going to change. Okay. So there are certain inputs to this. So again, remember from the examples of semantic modeling or the data modeling and those class-based modeling or object-oriented method that we use for requirement engineering, then whenever we borrow, there are two inputs. So imagine that we are borrowing a book. So the first input is that which book you want to borrow and who is the reader. So these question marks, so again the notation is the same. Here we have the identifier and here we have the type. So we know that the type is a book and the type is a borrower. And from this state space we know that in our system there will be books and there will be borrowers. And this P notation, it defines that there is a whole set of books. So we have a huge set of books, which is stock. So we have named it stock. Okay. And each book, whenever a book is on loan, there has to be a borrower against it. So it cannot happen that a book is on loan, and so this is my state space. And now I'm saying that I need to have an operation which I need to write formally using this Z language. So I'm saying that there is this, so I'm defining the schema for my operation, and here is the schema name. So this is my schema name, which I'm saying borrow, and I'm telling that I'm going to change the state of my system. So library state is going to change, and there are two inputs. So this is again the same. So we have this identifier here and we have the type here, but this question mark, this actually tells us that this is an input to this operation. So this operation has two inputs. Okay. So the first thing that this operation checks is that the book or my input variable book, okay, for example, Introduction to Software Engineering, this is the title of my book. So first thing that I am checking is that whether this book is in the stock. So remember, I have a huge stock, so I'm just checking that whether this particular variable, it belongs to my huge set of books, which is stock. So this is first thing I'm checking. And I have another set which I said is the set of books on loan. So I have another set which is the set of books on loan, and so I'm ensuring that the book that the user wants or that the borrower wants to borrow, it should not belong to the set of on loan books, because if somebody has already issued it, then I cannot issue it again. So this is the second thing I'm checking. And then I'm saying this on loan prime, there is this small prime sign here. So it says on loan and this symbol here. So this means that my on loan set is going to change, or my state is going to change. So I'm saying that on loan is equal to on loan and union. So I'm adding to my set of on loan books another book and a reader. And whenever this happens, then two things are going to happen. One, my set of on loan books is going to increase. Secondly, an association is going to be created between that borrower and that book, which is defined here. So whenever I am calling this on loan, I'm saying that first of all, on loan set is going to increase, and secondly, this book will be on loan to this particular borrower. But there will be no change in my stock set. So my stock stays the same. So this is how an operation is represented. First of all, you identify what is the state space, or what are the things that can change, or how I define the state of my library. So very simply, I know that in a library I have books and I issue books. Okay. And whenever I issue a book, I issue it to some user. So I identify all the things which define the state space of my library, and doing that, I've written this my state space, and then because I said that there can be schemas which represent the state space, and then there are schemas which represent the operations, and operations, they change the state of the system. So I have this borrow operation. Similarly, there can be other operations, that your library receives a new book. Then what is going to happen? So we are saying here that this is another operation. So this is my schema name, and remember, this is again an operation, and we are saying that this is again going to change the state of my system. So that's why we have a delta sign here. So a change in state, and we have another input. So this is input. So now what is happening, that my on loan set, nothing is going to change there, because I've just got a new book which I need to store in my library, or I need to update my library that we have a new book. So the only thing that is going to change here is my stock set. So what I'm going to do, I am going to perform a very simple operation where I'm going to say that my stock, first of all, this prime sign says that my stock is going to change. And what will be my new stock? It's a union of this input book. So this is what's happening now. So this is my new state, whereas my on loan state, there is no change here. So it is always a good idea to specifically mention that if a certain state is not changing, then you just say that the new state is the same as the previous state. Then there is another procedure when you're looking at this library. You have this return, that a book can be returned by a user. So again, we have this change in the state of the system, and we have an input that somebody comes to return a book. Then the book ID is important, or what book is being returned. So we have this input. So first thing we are checking is that whether this book belongs to my on loan set. So first thing I'm going to check is that whether the book input is in the domain of on loan set, okay, and whether there was a borrower associated. So that is what I'm going to check. So if that is the case, then what I'm going to do here is that I'm going to say my domain on loan is equal to domain on loan and this. So this operation, what this would do is, it would remove that association between the book and the borrower. So remember that my on loan state was defined as this, that this set has an association of a book with a borrower. Okay, but now what is happening, that this book is being returned, and when this book is returned, so there is no change in the stock, so I know that, so that's why I'm saying my stock, there is no change there. But this association, for example, you know, that same software engineering book and let's say Naveed here, so there was this association there, so that needs to get rid of. So what I'm saying here, that the domain on loan, and this sign actually means that my association that was there, it's being removed now. So I have a new set which does not have this, which does not say that software engineering book was issued to Naveed. So that is being removed. So so let's look at some key points, and then we are going to conclude our discussion in our lecture today. And in next lecture we are going to look at another example of specifying requirements formally, or we are going to look at another example of formal methods. That in terms of these requirement methods, number one, we know that there is no ideal requirement method. Okay, and system models can be considerably enriched by combining different techniques. We know that the different techniques, if used in combination, then we can annotate our model more, and we can put more information into a model. And object-oriented methods, they are very good example of that. That they have different kind of models, and by using those different kind of models, we include more information. We put more information about our system. And data flow model is based on the notion that system can be modeled as a set of interacting functions. We know that. The object-oriented approach is based on the notion that systems can be modeled as a set of interacting objects. So there is a difference in the way of thinking about the system. When we talk about data flow systems, we say that systems is set of interacting functions, whereas object-oriented approach says system is set of interacting objects. And the formal methods, they are based on mathematical principles and are intended to achieve a high degree of confidence that a system will conform to its specifications. And we have seen that the reasons why formal methods are not very popular, or the acceptance rate is very slow, is because, you know, people generally do not have an understanding for that. And moreover, in today's lecture, we started looking at we said that there are different formal languages. There are two kinds of formal languages. One are model-based languages, and the example is the Z language, which we started looking in our lecture, and that is what we are going to discuss in next lecture as well. And then there are other form of formal languages which are based on process algebra. In terms of Z language, we said that Z language describes the system in form of schemas. Okay, and there can be two types of schemas. One schema represents the state space of the system, and the other schema, they represent the operations of the system. And whenever we are describing the schema of any schema in Z language, it has three portions. So a schema has name, it has certain declarations, and then it has certain predicates. So whenever we are defining a state space, for example, we looked at the example of library. So a library state space declaration included that we have a set of stock, and then we have another set which is on loan, or set of books on loan. But this set is special because this set means that all the books which would be in this particular set, they are associated to certain borrowers. So it cannot happen that a book is on loan and there is no borrower against it. Okay, so this is actually very beautiful, because when we actually say that, so we are removing that ambiguity, that because if this thing is described in other system, then there may be ambiguities. But here we are saying that there will always be an association between a book on loan and a borrower. And in terms of predicates, here in the case of that library state space, we said that all this domain of on loan books, so the books, only those books can be on loan which is in our stock. So we said that the domain of on loan is a subset of stock. So that was a predicate, or that is the condition that our system should always conform to. So we cannot have so the state space, it actually defines that throughout the execution, my system needs to be in this particular state. So my system so all the on loan books, as I said, they need to be stored in that set on loan, and there need to be an association of each book with the borrower. Secondly, only those books can be on loan, only those books can be on loan which is a subset of this stock set. And similarly, the schema for operations was similar. We said that we would have a name of the operation. We look at the example of that if a new book comes into the library, then we said that there would be certain declarations. So the first declaration said that the state space is going to change, so library is going to change. And then we said there is an input, which is the book. So book is the input, and it is of the type book. And then what were the predicates in that case? So the predicates in this particular case was that my on loan set is not going to change. So that is what I know. So we can simply write that. But I knew that my stock is going to change. So what is the change in the stock? That previous stock would be increased by this new book. So this is how these schemas are defined. We are going to talk more about that, how we identify the state space when we are trying to describe a system formally in our next lecture as well. And we are going to look at another example of specifying or formally writing requirements using formal methods, or using formal methods for requirement engineering. We'll look at another example using Z language. So that is it from today's lecture. Take care and Allah Hafiz.